Good evening, gentle readers. Coming to you live from Seattle, Washington, from a desk with Ross Finlayson here today, May 29th of 2024. Moment and motion. Geometry is motion. Geometry and motion is this idea to help reflect that the moment is this central, the axis, the lever's fulcrum. That here it's been framed largely about the notion that the lever is the simplest machine of a sort, vis-a-vis something like the ramp or the pulley or the screw or the wedge, the simple machines, that the lever is this sort of simplest machine in the sense that it models the center of rotation and the centroid, or how we frame things in terms of what it is about which that the rotation is free, in a sense that an object in motion stays in motion and an object at rest stays at rest. Here that's been framed in terms of the V viva and the V motrix, where the V motrix is the most general notion that object in motion stays in motion, object at rest stays at rest. And then the V viva is this sort of action of the live motive force with regards to thing that, like a flagellate can somehow move through a liquid medium, or something like this, vis-a-vis not really having any aerofoils or hydrofoils with which to affect a mechanical advantage given a configuration of shape. And for something as how the bumblebee flies, how some of these other effects, which are visible and observable and reproducible in the classical scale, and not just in the quantum or in the scale of all the galaxies, make it so that there's lots going on with the very definitions of the fundamental physical quantities as they're usually said to be conserved in mechanics. And this is where moment and motion started with a discussion on waves. And the idea was to establish an exploration of the wave mechanics and the formalisms of the definition of waves as mathematical models of waves, and then as with regards to the attachment of mathematical models to physical models to help explain all these kinds of things. And then as it became developed some more, that explored both this wave-particle duality, then as well the notion of the orbits, that an orbit is a very natural sort of way to have kind of the outer view of what's otherwise the classical, which is just linear motion, with regards to then helping to express for the ways that things move in the course of their geodesy, the world lines, is what general relativity has, that is the way things at any given instant are destined to go, vis-a-vis any changes which any actor or dynamics might affect. That it went fuller into studying some of the descriptive and formulaic aspects of waves. Then as with regards to some study of the history of the definitions and the theory of mechanics, and then also with regards to the definitions of the moment and about what it means for something to come and go to rest, or to arrive at a given state of motion. Much of this has been talk about the ordering of the dimensional analysis, that there's meters per second or seconds per meter, and it's both, and that this describes velocity. And then as with regards to all the higher orders of acceleration, that for any smooth acceleration, it's very well established as by force equals mass times acceleration. Yet any actual application of acceleration must start at some point be zero and increase to some arbitrary one, and as does its higher derivative and its higher derivative, each of its higher derivatives of rates of change, instantaneous rates of change. So mathematics sort of, not to my knowledge, doesn't really have the usual extant deliberation on the infinitely many higher orders of acceleration. It's all just framed in terms of impulse and specific impulse and impulse at a moment. And so when that's not really adequate to capture mathematically all the input that is from the infinitely many higher orders of acceleration that result in going from 0 to 1, then there's something to be said for why having the mathematics of this kind of thing would go a very, very long way to helping explain so very many things. So from my perspective, that seems to be one of the most interesting things about the moments of motion is the infinitely many higher orders of acceleration, because it's mathematically so that it goes through all these things to have any change at all. The only constant is change. Geometry is motion. That the idea of trying to figure out what that is has been explored in a couple of different ways. So to establish that, then it's necessary to sort of establish mathematical features upon which it can rest as in a frame. And so in the earlier discussions of descriptive differential dynamics, there was a lot of talk about the identity dimension, which is just the idea of it's like a function on natural or positive or non-negative numbers that's for any given number of otherwise orthogonal dimensions has about a Cartesian basis in Euclidean space. That the identity dimension is just the line that's all the coordinates have the equal value through that. And then that's the origin. And it was explored how, to begin, that's a singularity on the envelope for all kinds of fundamental integral equations like the linear fractional equation and Clairaut's and D'Alembert's. And this was part of the discussion of the sort of difference between the integral equations and the differential equations, that either is kind of the solution to the other, but the plane curves of the integral equations and the solutions of the differential equations are two kind of different things. And they're approached in two quite very different ways, and they kind of have two different motivations, and one of which is to end up being sort of as algebraic geometries, and the other one is that there's a whole entire host of numerical methods and stopping off points to hand off the rest to the desolve function or to linear algebra routines, which results Runge-Kutta or Newton-Raphson or these various quadrature and cubature formulas of numerical methods, which can arrive at values of crunching the numbers without having to so much do the work of the algebraic and symbolic manipulation. Then another part of that was this complex diagram that arrived from inspecting the definitions of the complex numbers as usually ascribed to Gauss and Euler, and not so much getting into the telescoping solution that arrives at something like the reduced form or closed form that makes for Euler's identity, and not really to get into all these things about fun with complex numbers and e to the I pi and roots of unity and this kind of stuff. But the complex diagram basically noticed that division could be defined differently, and so it's just like, well, it has non-principal values, and so in this way, then you can map using that one quadrant for the identity dimension, or octant, or 16th or whatever it is, in each of these higher dimensions in this n-dimensional cube out of or if not so much a cube, at least like a corner of all these intersecting hypercubes or tesseracts, the origin of the Cartesian orthogonal space of Euclidean space. That the sides next to it fold out to make for this complex diagram, and to make as a sort of complement to the identity dimension and the establishment of more ideas about ways to make closed forms and completions for analytical series and this kind of stuff. Also ways to work in notions of alternation and oscillation, basically, as about that. So there's lots going on with that as an analytical setting. So what's the relevance here to moment and motion? Well, coming forward then into the moment of motion, then a couple ideas start getting established. And one is meters per second or seconds per meter. And this is about the dimensional analysis. Because on one side is displacement and the other side is velocity. Or on the one side is displacement and the other side is distance. So by the way, it's displacement in time, or whether it's distance over time. Same units, different interpretations, different meanings. So that's one of those things that is explored a little bit, because it really gets the dimensional analysis, which is the way things are set up in physical setups and ansatsa to arrive at things that end up making sense pictorially and graphically, and also with their attachment to the physical quantities as measurable. So meters per second and seconds per meter was explored for a while as for various interpretations and the various vagaries in their interpretations. That these vagaries make allowances for what could be read differently or what should be read extra to make it so that it would have a placeholder for what's otherwise these dimensionless quantities, to assign them as well dimensional character for analytical character, for real analytical character, for the mathematics of this thing. So then getting into the infinitely many higher orders of acceleration, one idea was this walk integral. So after some reading of the path integral and the sum of history, sum of potentials being the theory, I mean, a principle of least action is like, well, it's a principle of least action after everything in the universe has reached its point, and then everything in the universe moves on from that point. The clock hypothesis, and all parameterized by time or any other continuous parameter that happens to be modeled so aptly by time, which has never been falsified in any of big science's experiments ever. That the sum of histories as sum of potentials then makes for an overall thorough theory that geometry is motion is the same kind of thing, that it's a theory of sum potentials. That this is least action, and otherwise, according to all the conservation laws, which are framed as continuity laws, and for symmetry and invariance and symmetry flex and quasi-invariance, which are things, and in the field today, that this idea of the walk integral then is, after this notion of the dimensional and dimensionless resonator or alternator, that these are the ideas that at any given step, in any given course, that from any prior step, it's always modeled, there is for the prior and posterior is kind of what it's about. Because the prior will always have noticed a change, whereas the posterior will always have noticed an arrival. So it's with the notion of kind of what adds up to it vis-a-vis what it adds up to. That's what it really boils down to. It's how to make a complementary dual and frame the completions either way in both ways, from the total Machian universal sum of all potentials to a line, moving in a line with the classical impulse and constant acceleration. Those are the same. That as the great and most usual point of verifiability of Einstein's theory of relativity is it's classical in the limit. Right? So the walk integral is framed in terms of after the stop derivative. And so the walk integral is the idea that as things go forward and turns are made, it's always as of the narrow linear view of that, instead of the view as where it started from, because it's figured the body that's actually active is in its own frame. So that's kind of what it boils down to, that the meters per second and seconds per meter adds up and back and forth for this dimensional and dimensionless resonator alternator, that for any given moment it's linear and classical as it's going, every given thing, while at the same time it's all the many poles with respect to the poles and the axes all about and around every other thing. That the walk integral's goal is to result having that carrying forward, because all the geodesy got to be integrated all the time as going forward. So instead of for something like boost addition or just the Galilean addition, which it is for linear things, to have it this same kind of idea when the space frames and frame spaces of general relativity make it so that Lorentzian Fitzgeraldian space contraction is the most suitable metaphor for space contraction as a model of bodies that meet and part and pass and collide as in their orbits. So the walk integral came after the stop derivative, and the stop derivative is pretty simple. And when you think of acceleration, it's meters per second and meters per second squared and meters per second squared and so on. These, or meters per second cubed. You can see that it's also considered in these other terms. This is a reflection on the Mertonian school and the great argument of for V viva and V motrix, and also for whether power and resistance are differences or quotients. You can write it either way as long as everything adds up in the arithmetic. The only point is that it's linear. It's like, well, in the linear, the force equals mass times acceleration is in the same units as it multiplies on out and adds on up. Right? So the stop derivative is sort of the opposite of that. Instead of wanting to compute distance traveled in a straight line according to constant acceleration or according to velocity as a function of time, because the force that makes the acceleration is a function of time, then the stop derivative is basically that. It's like how far does it take for something to change its velocity to zero. And then as the one makes for integrating according to the power law, it's because it's the most usual directly known thing in calculus, how to compute the integral or derivative of a polynomial in or monomial, a power of a number, to reduce the power of the number. It's the most familiar rule in calculus to say that x, for the value of the variable given to a given power, its derivative is that number reduced by 1, and its integral is on the order of that number by 1. So this makes sense, is that, well, it's in line terms, it's in area terms, it's in volume terms. This is what integrates, and for a continuous domain like time. And similarly, it's how it falls down to make a derivative or the tangent is the other usual way to model an instantaneous rate of change or the slope of a parametric function of a curve. So the stop derivative is then the idea is like, well, when it reaches 0, then it's just 0. It goes flat. Once it gets to 0, what's its derivative? It's 0. Well, if you reach to 0, what happens if you take its integral? Well, guess again, it's 0. You know, it gets annihilated by the multiplicative annihilator. Kind of like the origin is the additive identity in the multiplicative annihilator. It's the singularity for division by 0. And it's all these different things to do with the envelopes of all these integral equations. Then there's that the identity dimension is this further envelope for all these linear equations. So the regular derivative also takes itself to 0. Kind of like dividing by a number infinitely many times. It's just that, well, powers are finite numbers, and so eventually it will go to 0. And then there's the idea that the for whole powers, and then the idea is that coming up from the negative numbers, it does not go to 0. It goes to ln x, like x to the negative 1. It's integrated, and it becomes ln x, natural logarithm of x. And this is very remarkable because it's like, well, if I just think of those as the whole powers instead, and this is for whatever reason it comes and goes this way, then why is it that it adds up to that instead? And especially considering the numbers, whole numbers, and then the positive and negative numbers, the integers, the Zahlen, go from infinity down to zero and from zero down to negative infinity. The idea of the stop derivative is that it bridges that gap there, because it helps to relay that just as something is coming to motion or rest, the idea of the stop derivative is making a smooth interpolation over that, and that's kind of what it is. So the walk integral then is kind of a complement of that, outside and later in terms of this dimensional analysis. And then there's these two other complementary concepts named abstractly, vaguely, just kind of in the mists of these things, that there's the pause integral and a run derivative. And that those to figure out that for something like, as from the readings from Einstein, that Nessie's hump is the way that the Loch Ness monster, which is a mythical creature, and when it's seen that it is a series of connected humps, half above the water visible and half below the water where it moves, that this basically affects to reflect on the notion of the walk integral and this dimensional and dimensionless resonator and alternator. So there's much talk of that in the development of the discussion of Einstein's, as he calls it, attack on Newton, in this idea of a Machian total field theory that's the sum of histories, sum of potentials, in classical in the limit. So that's kind of what's new in these concepts here. Anything else you can just find in a regular textbook. You can find in a thing, and just you can find it very readily, because the entire school of the linear curriculum is built up on very simple things up after the Galilean and after the Newtonian, and the system of the world and all this kind of stuff, and that's the way it is. I mean, that is the linear curriculum. That is standard. So these ideas I've been talking about are things that I'm not too sure of who else has invented or discovered it or discusses where, but if there's one thing that kind of points to that, is why it is so, it's because there's infinitely many orders of acceleration. Otherwise, there would be none. It's just Zeno's argument about that things that are in motion actually do move. This is that things in motion ever change motion. And the idea that geometry is motion is like, well, geometry, the giant pinwheel of a Cartesian orthonormal vector basis, is everything in motion about it. And that's just a nice thing for Platonists and strong mathematical Platonists to arrive at, for sayings that confound themselves, like the only constant is change. They're kind of true, and that truth is regular, and of course, whereas moments in motion are motion at a moment. So these are the things. So now I was trying to figure out some more about that and what I could kind of study for this or learn or come up with. And so what I've been kind of reading about a little bit was, one thing was this fractional calculus, or the extraordinary differential equations. So the ordinary differential equations can kind of be framed as like, well, they're linear, and they kind of represent terms in one or so powers of a variable in terms of each other. Ordinary differential equations. And so there's sort of ordinary integral equations as well. Although one may aver that the ordinary differential equations, the ordinary integral equations, in a sense, just being in terms of whole applications of the derivative, taking d dx, the derivative of something, taking the integral dx with respect to something, that's a full operation. So what are fractional applications of differentials and integrals? And this is called the fractional differentiation, and sometimes, or it's called I just was studying this a bit, or extraordinary differential equations. So the idea is sort of like other notions of interpolating between values, that you have an addition formula or something like that, or defining when an exponent, for example, is defined by multiply a number by itself so many times. Then there gets into defining, well, what's the negative exponent to a negative number? And it's kind of like, well, take the inverse of the number and multiply that by itself so many times. And there's the idea of, well, what's the root or the fractional of a power? Well, it's taken this such and such power over this such and such root. And so this gets into quite a definition of the entire great facility that still ends up having that the power law with the addition formula for powers of like terms in those fractional terms adds up. There's still an addition formula for it. It's not like there aren't definitions of fractional powers that don't have that as a feature. That wouldn't be very useful in a lot of senses, because the great utility of those is their addition formulas. And otherwise, being able to manipulate numbers and the arithmetization of it in terms of powers and roots, the operator calculus, and logs, and exponents, and the operator calculus, arithmetic, and all such matters of things that arrive at addition formula, and halving formulas and doubling formulas. That it's totally so that the main definitions of why those things are defined is like so, and first and especially because classically in the limit they're just for the integers. That these other definitions of the fractional sorts of roots and powers, for example, could end up having it so that they were so like in the middle, and they weren't really so for the integers. They kind of built the completion the other way. This is always something that can so be. So the idea of this fractional differentiation, or the extraordinary differential equations, if I ever wondered, there are ODEs and they're non-ordinary differential equations. And then these extraordinary differential equations are supposedly having sort of this fractional course that carries and interpolates what will happen is like at a moment's notice, or as with some root or power or log of that with which the change is with respect to, or that which is integrated, or the region, so that the terms that are derived for the quantities end up being still for those as well. So that's one thing that I came across and figured that would eventually be kind of relevant somehow. Like as it is, so if we're trying to figure out the stop derivative first, as just kind of getting over that hump, and then with regards to and reversibility, and then with regards to something like this walk integral, also trying to figure out what would be the needful for mathematics its objects to provide that would be sensible, fungible, and then tractable, to make it so that what it would so arrive at would be possible to use to formalize something like infinitely many higher orders of acceleration, or as many as you need, as many as there can be, enough to arrive at this. Then another thing, and this was discussed a little bit last time, I suppose, was the idea of dimensional analysis as often as done today. Because often as done today, it makes a sort of principal component analysis and is part of rank lowering, and used to, which is a key way to reduce the difficulty of a problem by framing it as a problem with less variables, and then solving that. And this is the Buckingham's pi theorem, as it's named for a fellow named Buckingham, if it was invented before by somebody else. that the idea is then that makes for a dimensional analysis for some kind of principal component analysis, and then sets up problems to be really solvable by a linear analysis. That's not the idea that was put forward here, but sort of this fuller dimensional analysis. It's like, well, eventually this problem we already have is kind of simplified, just with the classical linear formalisms. So there's a bit more to attach back to it to make it so that this dimensionless alternator resonator bit makes for this sort of approach to having a means to first describe something to make it sensible, and then to make it formulaic, to make it fungible, and then to put that into terms like with formulas and forms to make it tractable. So that was another thing that I've been studying for a while, or I looked at briefly and wondered about and imagined that would be relevant to so, and connected it to all these other related terms, because they live in an entire giant body of defined relation called mathematical Platonism. They exist, you know. And then as with regards to figuring that out, that the idea of the extraordinary differential equations is something that we'll see so follow. It reminds me a bit about the umbral calculus and the methods of differences, methods of finite differences. And again, another great, lesser explored field with many, many opportunities to solve many kinds of concrete problems. So I was studying that, and then the other thing that I looked at the other day for a while was the hypergeometric. So the hypergeometric was discussed a bit here in the descriptive differential dynamics and reading about the algebraic geometry and the integral equations. And so one of the key features of it is that it's said to reflect any kind of system with three regular singular points. And that then Gauss found one formula that kind of stands it up to 10 it out, to break it down to solve it out, involving factorial and a differential of a functional form with something in a given order of a difference of a couple terms, and then a given order another one. What results, of course, sort of series, and where the terms are based on a coefficient of a difference and a power of a difference over the factorial, and that this is the hypergeometric series. So that's kind of an approach to start working on methods for it, but that's quite a ways past where it takes to kind of just establish kind of what it's talking about. And so what it's talking about is any kind of integral equation that has three regular single points, and the most natural one are these ones that have the 3 points are 0, 1, and infinity. So 0, 1, and infinity are these three key, central, critical, and singular points that are part of the hypergeometric. And then it's declared or discussed. I was just reading the Wikipedia page about it, about hypergeometric functions, hypergeometric series, and a hypergeometric distribution, of course, is a distribution from probability theory with its own particular properties. And it's built as after the monomial and the polynomial and the various other terms, because everything is, you know. It was like, does it have formulas related to trigonometry? It's like, well, yeah, for thousands of years, trigonometry was everybody's formulas for everything. You know, that's the way things are. So as I was studying that, mostly I was relating that to the power terms, and because here there's this notion of there's Maclaurin and Taylor series, and then Clairaut and Fourier series, and so one's in differentials and the other in powers, and but they're infinite expressions. Basically, that's the formula. So you figure for any kind of infinite expression, infinite expression with the operation in the terms that diminish somehow, so it's might converge, you know, it's not obviously divergent, or just for the range of the values for which the operators are so. This is what we learned about from the singular equations, the singular integral equations from Neri, reading from Neri, in one of these books that I have sitting around here. That 0, 1, and infinity then become key values in this hypergeometric. Now, first, it's to be admitted that the infinity isn't a number you always see in these formulas or in these forms. And in fact, it's something like the differential geometers is like, not only are we entirely terrified of infinity and won't have it anywhere around, but also 0 is out. No, we just, everything is kind of, just has to be a smooth hump over this the class of continuous functions, so our forms are closed. It's like, well, that's great, but there are infinitely many higher orders of acceleration when anything actually changes, because otherwise you just kind of have a model of stasis. Differential geometry, not to poo-poo something which is, very, very useful in very, very many things, and especially when things are simple and linear. But it's just something to be said that infinity is the usual one of these three regular singular points in the sort of usual introduction of what's a hypergeometric. So I was led to recall that from the study of the integral equations in the ye old college textbooks from about 80 years ago or so, that this was the thing that everybody would have been learning in their college courses towards a mathematics degree in physics and dynamical modeling at the time, vis-a-vis that after like Leontief or whatever, and the idea that linear solvers solve everything, and you write some Fortran and make some linear code, and it makes a code, and then it can solve anything, in accordance to these numerical methods, that it's just kind of left out. So it's something that I'll be studying some more to help effect to relay that. Then it just kind of gets into the entire class of the symplectic and the manifolds and anything to do with regards to the dynamics of integral equations with three regular singular points, where it's said, then everything can be framed in these terms, and it makes a body of analysis, makes an analyticity about it, and it makes a way to express conformal mappings from any other problem with a similar such scope, and then to this and that for the hypergeometric, and then that Gauss's series, or it's just an example of a form among all these other many ones, and maybe that it's just like, well, it kind of dovetails neatly with Euler's formula, Gaussian integral complex analysis. It's like, well, that's great. But here we're looking at all the way back in the definition of complex numbers themselves and saying, hey, we can unfold this division left and right, and start with two things at once. That is kind of the idea, to consider how to make it so that then for something like this Clairaut-Fourier analysis and Maclaurin-Taylor analysis, where Clairaut and Maclaurin are for the trivial, or for the zeros of the solutions of these series and the infinite expressions, Fourier series and Taylor series, that the idea is then that there's a similar one, then getting into this notion for the hypergeometric is about that, and that being about the singular points, the envelopes and such like that. Now we talk about this fractional calculus, and also for this other stuff to do with any other kind of term, and making series for those for forms, and those with respect to things like this hypergeometric series, that all has to eventually kind of relate to the geometric series, like the inverse powers of 2, they sum to 1, it's half and half and half again, summed up together, makes the idea of this rate of change that is proportional to the rate. And so maybe that's a good way to think about the higher orders of acceleration as starting and stopping. So we talked a little bit about these talks in moment and motion and descriptive differential dynamics, and about Einstein and the train and the lake and the vision there. And then there was some talk of these formulas and forms of the classical mechanics, and the reasons why it's not exactly the same meters per second and meters after so many seconds. The difference between distance traveled and velocity, and this and that. So now the idea was that for the moment and change was the starting and stopping and the classical exposition of the geometric series, or the half and half and half and half again. So when we think of force as mass times acceleration, here the idea is thinking of an abstract thing that is whose velocity is proportional to the time traveled, or as the distance is proportional to the time, or as with regards to that coming to a stop in the first time period it loses half its velocity, and the second it loses half again, and the second loses half again. So after infinitely many moments of time, it will have reached a stop. It will have achieved a distance of 1 while it would have velocity of 0. So the idea here is to make another attachment to Zeno's arguments about that. First, we just kind of say, well, we have something like line reals or like iota values. We've divided a unit interval of time into uniform segments that are infinitesimal. So we have this, and then it comes in very fast when it's arbitrarily fast to when it reaches arbitrarily 0. So as of leading up to a collision or to just coming to rest otherwise. Because the idea is then a scale that like any change from A to B, from V at A to V at B, is going to be framed this way. So this is the idea, and I'm not sure if I've really explored this before. The idea that it's possible to thus make it so to attach for this idea of the infinitely many higher orders of acceleration, at least this idea that there's infinitely many steps when something goes from velocity A to velocity B. And to generally reduce that to that it goes from 1 to 0, and it does that in a distance from 0 to 1. But to keep those in separate terms, because even though then their units would just all cancel out, they're just like they fractionally do, or they incrementally do, or in the series they do. So this will be something I'll be thinking about a little bit more. So I'll be trying to figure out a name for it, an idea, where the idea is it's kind of like Zeno's something about Zeno, because Zeno of Elea and this Eleatics is like, this is an idea that it's not the different idea that people would be sitting around thinking around the fire when they're trying to formalize and make their theory and their axiomatics and their reasoning of these things, and mathematically with proportion and geometry as motion for all these things, is the idea to associate that this is not something that would happen so much as accords to it's that it's not contrived. It's very contrived. The geometric series itself is sort of the least contrived sort of thing. It's like, well, time is infinitely divisible. So in half the time, for constant velocity, in half the time, it goes half the distance. It goes half the remaining distance in half that time, and half the remaining distance in half that time. They both sum up to 1. And the fact that it's all universally parameterized by time, it is so parameterless and that dimensionless equals 1. So here the idea is that it's like in the half amount of time, all occurs in the first instant. So now it's taking what's the infinite series and then writing it kind of like we have the geometric series, where all the entire significance of the first term of series is the most significance, all the way to the least, and vice versa, because either way, it's kind of like in mathematics, people look at a series like The geometric series of this inverse powers of 2, if that's supposed to affect or reflect on Zeno's argument, is like, I got to take half the time to count the next smaller bit of series to add them all up. Right? Instead, we can just say it's like, as long as you consider the entire infinite series, it's really a parametric form, and it equals solution 1 over b minus a, or as 1 over b minus 1, as it were. That here the idea is to start framing it for this infinitely many higher orders of acceleration as to have a uniformization of that. So that's the new idea. It's sort of part of the idea of the infinitely many higher orders of acceleration. So it's kind of like an infinite series with as well infinite terms in it. But that's it's got to expect some relation and proportion to help express to relay that yes, this is entirely contrived, because it isn't really something that happens. So just like there's not ever really just a classical linear impulse that goes from 0 to 1 in an instant, although everything is modeled that way, because force is really a function of time, not just the instantaneous impulse at a time. Then this idea of this fitting function for these infinitely many higher orders of acceleration modeled as a continuous change is what, and now that's my new idea for this series. So the idea is to figure that in terms of series terms, and then to make it so that it mostly reflects on the geometric series, and about how there's one series where it starts with half and then goes to all the inverse powers of 2 smaller and adds those up, and the other one it starts with nothing and then grows and adds that up, and they both point and reflect back at each other in the middle. See, so this is part of the complementary duals, meeting in the middle of nowhere. Over the past 100 or so hours of these talks, these are the kinds of things that are part of the mathematical milieu throughout. Whereas this idea of the function fitting, infinite, double series, Zeno's infinitely many higher orders of acceleration in a box is now what is my new idea of these ones. After this, something like the identity dimension and Nessie's hump, and that will lead into the next sort of bit of this talk, I suppose. And then the complex diagram, and just showing that the integral analysis and differential analysis have lots to explore, and indeed lots in the middle that kind of is defined and defines both of those. And then there's something about these other aspects that have been considered here as ideas, and is learning has helped to uncover where these things already are, things like the singular integrals and the LP spaces and the theory of functional theory and functional transforms, and the convolutional setting, as was discussed, and the things about the singular points and regular singular points, and algebraic geometry, and Lifshitz and Picard, and these kinds of varieties, algebraic varieties and algebraic geometry. Then as with regards to this symplectic manifolds and symplectic geometry and the hypergeometric and the regular singular points, they were kind of pulling away from that being all about Gauss's series, instead making it more so about the analytical setting, the analyticity that could well be still also something like that. That these are the things to help figure out meters per second or seconds per meter. Where last time it was basically figured out, it's like, well, when you're going more than 1 meters per second, it's meters per second. And when it takes more than 1 second per meter, it's seconds per meter. This is kind of the idea that this doubling side on either side comes and goes for power series. And then I'll probably look a little bit like e to the x and e to the minus x. And then they have the doubly infinite series in mathematics. X squared plus minus 1 was also a good one. I was trying to figure out some more the other day. And also defining the trigonometry secondarily and coming up with a side approach to trigonometry that wasn't the same as the way that everybody learned in school. But so it can still arrive at making the objects of geometry without necessarily the same apparatus at all. This is another thing that is kind of amusing. Then the other thing to talk about after that, so winding down, is the pseudomomentum. So the pseudomomentum is that in the idea of this dimensionless resonator alternator is to help support the definition of what after inertia, which is defined by velocity, mass and velocity. It's in terms of mass and velocity. And momentum, which is defined as like as of the integral of that. Yeah. What this means to make for this walk integral is like a momentum integral too. And it's to make for something like the pseudo-momentum, and why it's not a real quantity yet it's still supposedly conserved, to get it back to its inertia that's conserved. Because as it is, it's like, well, force equals mass times acceleration, and then that's in the terms that look like inertia, momentum, excuse me, trying to keep all the units straight and all this kind of stuff on the same terms. That the idea of the pseudo-momentum and the walk integral is that it makes sense why the very definition of the things still so seized to arrive at that these contemplations of a deconstructive account, and it helps a lot to have a mathematical foundations at least that's got these extra pieces in it, if you know what I mean, fuller picture, more complete. That then this deconstructive account is still making for things like symmetry, invariance, and conservation law as symmetry, flex, quasi-invariance, and continuity law. Then that momentum becomes, as pseudo-momentum, sort of a not quite virtual and not unconserved, but only sort of eventually conserved. That the system is wider in terms of this sum of potentials and potential theory overall. The fields of potential are real, is what's real. That then for the classical, that as momentum is classical and torque is dynamic, that instead torque is static and momentum is virtual. While at the same time, this resonator alternator still always classical and existent in a straight line. Then as for the rotational, that you get rotational momentum and spin momentum and spin. That this is a way to help establish the descriptive definitions necessary to improve the theory of classical mechanics. Which on the one hand, when it's first explored as the Galilean and velocity and these kinds of things, is just so perfectly fulfilling, especially with some notions of calculus. It's like, I can definitely compute A to B and the time the train takes and all this kind of stuff. But then later starts to just fall apart and start becoming just kind of mysterious, and perhaps it's just I really don't know it very well. But a lot of the stuff that goes in mechanical engineering is contrived, and a lot of the rest of it is tribological, and it's very empirical. And so trying to help establish any way at all that these things are so and like so, and then especially to arrive at sensible, fungible, and tractable as a model of these here with this kind of approach to, just continue with Zeno's series and so on to carry that forward. That's going to be kind of thing. So I haven't come up with much yet, but that's what it is for today. And I don't really spend too much time trying to figure things out, but this act of extemporizing sort of helps for it to arise and bring it out and bubble it out. And the other idea, I guess, was looking at was quantum particles and spin. So the idea is that there's the spin of particles. You think of it as kind of like in a rotational setting, you'd think of it as being like the moment or the torque they would make braking something, or the torque they would make on the axis, or these kinds of applications of force. And the momentum is quantity and supposedly conserved quantity, and so these half spin particles, and then these spin 2 particles, or the fractional spin of the particles, basically affects to reflect an interesting feature about the field, because it's kind of like something about an electron or a quantum particle with spin 2. Is that it takes 2 spins around it for it to reach the same equilibrium state, as if it were kind of wound up in a way that preserves its orientation with respect to its free rotating frame, that is free in its frame to rotate twice as many. So in the particle mechanics and the continuum mechanics, what this relates to is the doubling spaces and halving spaces of the continuous and discrete, that is at this level of the particle and of the particles in the aggregate in the field, why the quantum particles have these properties, and that they are integer properties, which would otherwise just be 1, why they're not 1 and why they're half or 2, is as of affecting a reflection on continuum mechanics and the difference between the discrete and continuous from the line reals to the signal reals, as of a doubling space, so sorts that the points in a line double to the points on a line. And then for the signal reconstruction, that's kind of a halving space, otherwise comes into kind of the complete ordered field, or otherwise into about the line. That was the other idea that I had, was to help explain quantum physics and the existence and the properties of particles of half integer and integer spin, as with affecting a reflection on mathematical topos and functions for this quasi-invariant symmetry flex. That's all just a simple fact of continuum mechanics, because the mathematics objects, the numbers, have these properties, and they just give these, and then they add right up. Well, I shall so hope you had a great day today. It was sunny today. It rained a while. The wind came up a bit. It's cool now. Hey, have a great day. To your health.